Okay, so now here we will discuss some advantages of MIMO antennas. So it has higher data throughput by transmitting multiple data streams simultaneously across multiple antennas. MIMO drastically boosts the overall data rate, making it ideal for high bandwidth applications like video streaming and large file transfers. It has improved signal quality also. MIMO leverages multipath propagation where signal bounce off different objects in the environment to create multiple signal paths, thereby reducing the impact of signal fading and improving signal strength. Extended coverage. The spatial diversity provided by MIMO antennas helps each areas with weaker signals, enhancing network coverage in challenging environments. It also provides the time diversity, means the packet data can be different time slots, means the packet data can be put in different time slots. Frequency diversity, different frequency channels can be used for transmission also in this MIMO system. And enhanced reliability. The redundancy introduced by multiple signals passed in MIMO system improves the overall reliability and robustness of wireless communication. So here is some applications of MIMO antenna. It can enhance the Wi-Fi performance. So actually most modern Wi-Fi routers utilize MIMO technology to achieve higher data rates and better coverage within a home or office by sending and receiving multiple signals simultaneously. Cellular network capacity boost. MIMO is a cornerstone of 4G LTE and 5G networks, allowing for increased data speeds, improved network capacity in crowded areas by efficiently managing multiple signal paths. MIMO also provides improved signal quality in challenging environments. MIMO can mitigate the effects of multipath fading, which is a common issue in urban environments where signals bounce off buildings. By exploiting these reflected signals, we enhance signal strength. Autonomous vehicles. Actually, autonomous vehicles such as self-driving cars rely on wireless communication systems to exchange data with each. So in this kind of traffic infrastructure and cloud servers, MIMO antennas are used to ensure reliable and high-speed communication, enabling real-time updates on road condition, traffic pattern, and navigation instructions. Drones. Drones are becoming increasingly popular for various applications, including aerial photography, surveillance, and delivery services. MIMO antennas are used in drones to establish stable and long-range communication link with the controller or ground station. This allows operators to control the drone from a distance and receive real-time video feeds. Satellite communication. Satellite networks are increasingly adopting MIMO to enhance the data transmission rates and reliability across large geographical areas. Internet of Things. Multi-site deployments where numerous devices need to communicate simultaneously. MIMO can help manage data traffic efficiently and improve network capacity. So here is the designed MIMO antenna in our lab. So this work describes the semicircular multiple input, multiple output antenna with two reconfigurable band notches as WiMAX, that is 3.3 to 3.7 GHz, and WLAN, that is 5.09 to 5.93 GHz frequencies. So then design antenna comprises of two semicircular monopole antennas with tapered shaped microstrip feed lines connected on the lower part of each monopole. The substrate, the substrate composed of FR4 with a height of 1.6 millimeter and a dielectric constant of 4.3 is etched with these two radiating structures. The S11 parameter of the antenna exhibits wideband frequency coverage of 1.5 to 13 GHz representing an impedance bandwidth of 158.62%. The design memo antenna demonstrates excellent characteristics such as low mutual coupling, high impedance matching, and the potential for RF energy harvesting applications, which we will discuss later. Now, we have introduced band notch functionality in this MIMO system. Actually, band notch functionality is necessary to prevent electromagnetic interference between UWB technology, which has a range from 3.1 to 10.6 GHz, and the pre-existing wireless systems. So it can be accomplished by etching various notches and adding parasitic elements in the UWB monopoles. Here, the radiating patch is integrated with modified C-shaped slots to attenuate signals in the WiMAX band, that is 3.3 to 3.7 GHz. Additionally, rectangular split ring resonators are positioned as parasitic elements near the feed line and radiating elements to reject the WLAN band, that is 5.5 to 5.92 GHz. The proposed antenna can be modified to act as on-demand filter whenever interference needs to be reduced. It includes reconfigurable dual band notches, which is achieved by inserting RF pin diodes on the modified C-shaped slot, and rectangular SRR to realize the reconfigurable band notch characteristics. So this is the fabricated prototype of our MIMO antenna. And SMP1320 pin diodes, they are mentioned at D1, D2, D3, which are individually connected in series with the notches, with the notching structures, and provide notch band switching when switched on. Diode D1 is placed in the C-shaped slots, and diodes D2, D3, D2 and D3 are placed on the two split ring resonators close to the feed line. Here we will discuss the mode of operations. So this MIMO antenna can be used as reconfigurable MIMO, where the reconfigurable band notches can be used. How? For example, when all the diodes are switched on, means diode D1, D2, D2 and D3. So here D1, D2 and D3. So it is switched on, it is switched on, and it is switched on. So we are naming this as mode 1. So whenever all the diodes are switched on, the notch structures will be shorted and will be deactivated. So, yeah, ma'am, am I audible?
Yes, sir.
Okay, thank you. So, when all the diodes are switched on, then the notching structures will be shorted and will be deactivated. So, notching structures will not work. So, what will happen? As the notching structure will not work, we will get the full bandwidth on the antenna system. Means 1.5 to 13 GHz band will be achieved when all the diodes are switched on. So I'm repeating again, when all the diodes are switched on, these notch structures will be short-circuited and will be deactivated, and they will not provide any kind of notching mechanism to the antenna. So the antenna will have full range of its bandwidth, that is 1.5 to 13 GHz. Now in mode 2, when all the diodes are switched off, means when all the diodes are switched off, then the notching structure will be activated and they will give notching mechanism at both the frequencies, that is WiMAX 3.3 to 3.7 gigahertz and 5.09 to 5.92 gigahertz WLAN band. At the same time, the antenna will provide bandwidth of 1.5 to 13 gigahertz, but it will show the notching effect at these two frequencies. Now, I am coming to mode 3, when diode D1 is off and diode D2 and D3 is on. So whenever diode D1 will off, then this notching structure will be activated. So this notching structure is dedicated to notch the notch band of 3.3 to 3.7 gigahertz. So at that time, at this mode, the 3.3 to 3.7 gigahertz band will be notched out. And as the diode D1 and D2, D2, D3, D2 and D3 is switched on, so these notch structures will be deactivated and the notching mechanism at WLAN band will not be effective. So at this mode 3, only the antenna will provide notching at WiMAX band with the bandwidth of 1.5 to 13 gigahertz. Now, I am coming to mode 4. In mode 4, diode D1 is on and diode D2, D3 is off. So whenever diode D1 is on, this D1 notching mechanism will be deactivated. Means the diode, so this notching structure will be deactivated, means it will not notch the WiMAX band and it will only notch the WLAN band, which will be which are contributed by this notching structure. So we can see that the diode can be operated in 4 modes, where by using these 4 modes we can reconfigure the notching mechanism. We can reconfigure the band notching mechanism of the antenna itself. So now, here I am discussing the ground plane structure of the antenna. So we have designed a simple semi-elliptical ground plane which is positioned on the backside of the substrate. So using a notch-loaded elliptical ground plane helps to reduce the capacitive effect and increase the bandwidth of the designed antenna. Initially, the first 2 rectangular strips are added to the ground plane to minimize mutual coupling and to improve the isolation between the 2 radiating components. Then a chain of split ring resonator, you can see a chain of split ring resonators, in short, which is called the SRR structure, is also attached towards the lower section of the ground plane between the strips. As a result, the split ring resonator type structure between the ground planes is critical in enhancing the isolation of the proposed MIMO antenna, which lowers the mutual coupling, or we can say which lowers the mutual interactions between the 2 antennas. So the amplified view of the split ring resonator of the isolation structure is shown over here. So now here we will discuss the S parameters of the antenna. Here this is the S11 characteristics, means the bandwidth characteristics of the antenna is shown. It is plotted in the y-axis S11 is plotted and in the x-axis frequency is plotted. Here we have plotted the S21 characteristics. The S parameters show the bandwidth ranging from 1.5 to 13 gigahertz with an isolation between the 2 antenna elements is below minus 15 dB. You can see this is the minus 15 dB range. So the isolation between the 2 antennas is below minus 15 dB for the entire operating bandwidth. It also provides band notching at 3.3 to 3.7 gigahertz, that is the WiMAX band, and 5.09 to 5.92 gigahertz, that is the WLAN band. Band notch functionality is necessary to prevent electromagnetic interference between wideband technology with the pre-existing wireless systems. It can be done by etching various notches and adding parasitic elements in UWB monopoles. So here we have described the current distribution on the monopole and the notching structures. So here you can see the modified C-shaped slot at 3.5 GHz and two parasitic ring resonators at 5.5 GHz concentrate the current distribution most significantly at the corresponding notch frequencies. The vector current flowing along the flowing along the two sides of the slots and within the parasitic elements exhibits opposite directions, leading to cancellation effect. We can see in the notch structure, currents are flowing in the opposite direction in the outer side and the inner side of the structure. So a cancellation effect will occur. Consequently, the radiation from the current on one side is cancelled out by the radiation from the current on the opposite side, leading to no radiation and low return loss at the specified notch frequency of Ymax and WLAN band. The current distribution reveals that the proposed antenna successfully incorporates band notching at the Ymax and WLAN frequency band. Here we have done some kind of parametric study. Here LN1 and LN2 represent the slot length for achieving band rejection centered at Ymax and WLAN frequency bands. The parametric analysis of LN1 reveals that by decreasing the slot length below 28.4 mm results in a shift of the center of the notch frequency band towards the higher frequency range. In contrast, if we increase the slot length beyond 28.4 mm, then the center of the notch band also moves towards the lower frequency band without affecting the other frequency band. Hence, 28.4 millimeter is the optimal slot length, providing a notch band at Ymax band. The parametric analysis of LN2 shows the central frequency of the notch band shifts towards the lower frequency band if the gap length increases beyond 15.6 mm. If the gap length is reduced below 15.6 mm, the center of the notch frequency band moves to the higher frequency band. So a gap length of 15.6 mm has been chosen as the appropriate slot dimension for creating band notch centered at the frequency of the WLAN band. So here we have discussed the effect of the ground plane. This is the simulated S21 parameters for various ground configurations. This is for ground 1, this is for ground 2 with rectangular strips, and these the chain of split ring resonators are there. So here we can see we are a decreasing or we are having an improving value of S211 whenever the architecture of the ground plane is being improved by inserting chain of split ring resonator as well as rectangular strips. Another important factor in the effectiveness of the design antenna is the ground plane, which is positioned on the opposite side of the substrate, which I have told earlier. It also improves the isolation between the two antenna elements. So here we have shown the current distribution in the ground plane to understand the radiation mechanism of the antenna. The variation in the current distribution on the ground plane at 7.5 GHz for different geometries, that is for the initial ground plane with the I-shaped strip on the ground plane and with the chain of split ring resonators placed between the strips. When a chain of split ring resonators is etched on the ground plane and shows how much current is restricted when port 1 and 2 are excited as well as terminated. Here we can see port 1 is excited and port 2 is terminated. So resulting in a significant decrease in the ground current as compared to figure 9A to 9C. So we can see whenever port 1 is excited, most of the current is being coupled in the secondary ground plane or in the ground plane in the left side to port 2. So whenever we have introduced these structures, so lesser amount of current is being coupled to the port 2. And whenever the complete architecture using split ring resonator has been implemented on the ground plane, we can see ideally zero mutual coupling has been occurred from port 1 to 2. So we can tell that in this MIMO structure, two antennas will be completely isolated if we use this kind of ground structure using SRR. So here the complete fabricated prototype of our antenna we have shown. So you can see this is the back side of the antenna and this is the front view of the antenna. You can see pin diodes are shouldered over here in this notching structure, this pin diodes. So the same type of pin diodes should also be shouldered over here, but for experimental purpose, we have used only one antenna for the same. So this is the ground plane on the this is the back side of the antenna where we can see split ring resonators are there in the ground plane, and we have used a simple coil for the comparative to show the compactness of the antenna. So this is the different modes of the antenna which I have already discussed earlier, and this is the S1 characteristics at different modes of the antenna. Now, so it is a simple MIMO antenna. We need to know the contribution of envelope correlation coefficient and diversity gain. So, what is envelope correlation coefficient? Envelope correlation coefficient, or in short ECC, which stands for envelope correlation coefficient, which measures the level of correlation between the signals received from different antenna elements. A low ECC value, ideally close to 0, signifies good isolation between the antenna elements, which is desirable for optimal MIMO performance. A high CC value indicates significant signal correlation between the antennas, reducing the diversity gain. Ideally, ECC should be close to 0. Another important term in aspect of MIMO that is called the diversity gain. Diversity gain indicates the improvement in signal quality achieved by utilizing multiple antennas with low correlation. Especially or essentially meaning a higher diversity gain is better when the ECC is low. It represents the improvement in signal quality achieved by utilizing multiple antennas with low correlation. It is measured in decibels in dB, which is a higher diversity gain means better resistance to fading and improved signal reliability. So I'm repeating once again. So what is diversity gain? Diversity gain it will indicate the improvement in signal quality achieved by utilizing multiple antennas with low correlation. So here the plot of the envelope correlation and diversity gain. So we have seen that uh, we have got a higher diversity gain almost near about 9.95 dB, and we can see the ECC value is much lower, and the simulated and measured ECC values are less than 0.01, which indicates that the proposed antenna offers outstanding characteristics such as lower correlation and higher diversity gain. So here the efficiency and gain plots of the antenna has been shown. So this is the efficiency plot. We can see the efficiency and gain both are suddenly dropped at the notching frequency, means the efficiency and gain will be much lesser in the notching band or the notch frequency, which will result in minimal radiation, or we can see no radiation at the notch frequency. So here the E and H plane radiation patterns of the antenna has been shown. Actually, theoretically, a antenna which is being used for energy harvesting should have kind of omnidirectional radiation patterns, right? But practically, it is not possible for any kind of antenna. Any ideally antennas should give an omnidirectional radiation pattern, but practically it is not possible. So some kind of scattering mechanism will always be there. Some tapering will be there in the E and H plane radiation patterns. We can see that several tapering are there in the radiation patterns. So here we have also plotted the cross polars level. So actually, theoretically, there should be a quite good difference between the all. There should be quite good difference between the copolar level and the cross polar level, and we have also achieved a good difference or good separation between the copolar level and cross polar level, which is very much ideal for NIM operations or operations of any kind of radiating systems. So at last, this is our radio frequency energy harvesting setup. So this is our MIMO antenna, numerical configurable antenna. We have fixed the antenna, one single side antenna in this energy harvesting board P21 triple X CSR EVP. Actually, the energy harvesting rectifier, the rectifier part can be designed in our own PCB in using our own ADS software, or people can directly purchase energy harvesting board that is called the P21XXCSR EVP board, which can directly harvest energy at different frequencies, starting from 2.4 gigahertz, 5.5, and so on. So different ports are there for different frequencies. We can see. So here our intended frequency is 2.4 gigahertz. So we have inserted our antenna in the port of 2.4 gigahertz, right? So this is the multimeter. So now we have measured the same in our lab. This is the Wi-Fi module. In our internal laboratory environment, we are almost getting 4.8 volt from this harvesting system. But thing is that in the ambient nature, we may not get this 4.88 volt. We have done this experiment only for the laboratory purposes. So in outer cases or in outer environment, the you can say that the achieved voltage may be much lower. So this is the conclusion. So the antenna can be used for wideband applications. We have achieved impedance bandwidth from 1.5 to 13 gigahertz. So it is almost equivalent to 158.62%. It also reduces mutual coupling below minus 15 dB between antennas, and it also improves the isolation between the two antenna elements. It also achieves band notch at WiMAX and WLAN band. The effectiveness of the proposed antenna is helpful for Wi-Fi or LTE applications as well as wideband applications. Additionally, the radio frequency energy harvesting efficacy of the antenna may be useful for LED arrays, sensors, electronic watches, and energy storage devices such as batteries and supercapacitors. So this is the related publication from our lab. So here Mr. Pooja Das is my research scholar, and I'm the supervisor of her. So these are the references. And at last, thank you. So here I am going to end my slide, and I will now request participants to raise their questions, and I'll be happy to answer. Thank you.
Good evening, sir.
Yeah, good evening.
Sir, how to buy spin diode?
How to buy a spin diode?
GG.
Actually, sir, the thing is that biasing, we have used pin diode for switched on and switched off. If we put just 0.5 volt to the pin diode, it will switch on, okay? And if you put
GG.
0 volt, it will switch off, right? So you just
जी
need a simple voltage source to provide 0.5 volt to make the pindar switched on. It will be done.
okay
Sir, good evening,
Yeah.
sir.
Good
Uh,
evening.
Sir, in antenna design, we can model antennas in HFS or CST software.
Yeah.
In ADS software, I will notice that we can model the antenna in a RLC model also, sir.
Yes.
My question is, any reference books are available to design the antenna in RLC model?
Yeah, it is
Because
a very good question, and I think there are so many controversies are there among it. Actually, let me tell you, you will not get any book where the RLC circuit, the equivalent RLC circuit of the antenna has been shown. How to do it? It is not written or described anywhere. Okay, so by your own concept, RLC means it
yes,
is
sir.
a series or parallel RLC resonator. So antenna is nothing but a simple resonator which will resonate at a particular frequency and it will radiate. Right now, am I
Yes,
audible?
sir.
Am I audible? So now you
Yes, sir.
need to
Yes, sir.
you need to define the corresponding RLC, the combination of the RLC circuit by your own idea only. There is no hard and fast rule. So,
Okay,
so
sir.
as per the antenna structure will change, the corresponding RLC circuit will also change. So the thing is that in many publications you will see they have shown the equivalent circuit of the antennas, but how they have came to the conclusion or how they have done the equivalent circuit is not written anywhere.
Yes, sir.
Am I right?
Yes,
So
sir.
this is my observation I am telling you. Many paper I have seen that this is equivalent circuit of the antenna. So they have directly done the thing in the ADS and they, by using the approximate RLC or series RLC parallel circuit, they have got the resonance frequency which is quite antenna itself, and it is said that
Yes,
this
sir.
is the equivalent circuit of the antenna. Help you
Yes,
can
sir.
get, I think that the best help you can get from YouTube videos.
Yes, sir.
This is my
Yes, sir. Thank. Yes. Hello.
and in ADS actually in ADS you cannot design antennas. ADS will be useful only only for circuit design, right?
Yes, sir.
But
Yes, sir.
for structural antenna design you need to go for CFT and HFSS. And
Yes, sir. Yes,
for
sir. Yes, sir.
beginner, CFT will be much easier. For
Okay, sir.
beginner, CFT will be much easier, not HFSS.
Yes, sir. Thank you, sir.
Thank you very much. So any other questions?
Hello, sir. Good evening.
Good evening. Yeah.
Yeah, your session was very interesting, and I hope everybody got lots of information here. So I have a few questions. The first question is like you have used for energy harvesting one board, that is P21XX CSR EVB board, right?
Yeah. Yeah.
That is available in the market, or how you developed that?
Yeah. Yeah. It is available in the market, and we have purchased. I cannot remember the name. It is available in India also, but they are being imported from outside.
Outside. Okay.
And they will whenever we purchase online, they will impose the import duty also. And as a whole, it costed around 26,000. Miss Pujada, are you there?
Yes, sir. Actually, it was ordered from Mauser Electronics, and it cost
Yeah.
around
Uh-huh.
The
above
cost?
40. Sir. Above 40.
Above 40,000 it will cost, sir. The thing is that.
Okay. And it will
It will
support
cost.
like 4 antennas at a time. Like we can 4 or 5 antennas. I think I saw different ports, right?
Sir, actually it will support almost 5 to 6 frequencies.
Okay.
5 to 6 frequencies starting from 2.4, 3.3, 5.6, and it is very much efficient.
Okay.
And the efficient the board is, you cannot get this kind of efficiency by using your own rectifier circuit.
Okay, that's great to hear. Yeah.
That is that.
Very interesting. And the second thing is like, see, even this question I have many times in my mind. In most of the papers, when we write, no, when we write for the publication or kind of thing, people will ask for an equivalent circuit. And ultimately, when it comes to like the realization, we will go with the antenna or any filter with a normal like transmission lines only. We will never go and touch upon equivalent circuit model, isn't it? I don't know why still people will ask for equivalent circuit. Can you just derive for that?
Sir, actually, also, in my opinion, in antenna engineering, there is no value of the equivalent circuit.
But still people will insist that this is, most of the times it hits my mind. Okay, why? See, ultimately we will not use any like RLC components in antenna
Yeah,
when it comes
yeah,
to
yeah.
applications. But still, when research scholars will write a publication, or they will insist, okay, you write a equivalent circuit. When there is no value for it, why it is so much?
No, yeah. Sir, it is my, I also agree with you. So also in my publications, I have not used any kind of equivalent circuit. It is totally useless. If you want to, you can say that if you want to categorize the antenna in the broader manner, you can use it. But the equivalent circuit will make your paper lengthy, and then your paper will look much informative. That's all.
That's even my opinion.
That's all.
Other times I felt the same thing, but you touched upon that point here today.
Yeah, sir. And also you find that many papers have just derived the equivalent circuit. Have any paper told how they have got the circuit? No.
That is always like a try and hit and run method. They'll
No.
do a parametric analysis and finally they'll arrive at some numbers. And they will. This is what
If I am doing a research, and if I am giving some kind of equivalent circuit, so I should let the people know how I have got it. This is my opinion. So yes, just people are giving blindly the equivalent circuit and telling that we have characterized the antenna in this way, and that is I am not satisfied with this kind of research mechanism.
Yeah.
Thank you, sir. So any other participants? So also, I would like to tell that simple antenna simulation and giving the simulated and measured results and radiation patterns will not a good research approach nowadays. Yeah, it was a quite attractive research approach if you go back 20 years back. But nowadays, you not get any good research paper only doing if you do research on simple antenna systems only. You need to import other harvesting techniques or other real-life techniques into your antenna system.
Yes, sir. That
So
is
it means, yeah.
Integration of different technologies is always an added value.
Yeah, without integrating, see, sir, actually, if you are from the academy, then nowadays in the academic, the main purpose is you need to get project funding.
Yeah.
Actually, research publication is only a part of our academic.
Correct.
It now became only the part.
Yeah, most of the work that what we go, it will go to the shelves, not for the academic research, especially. So it will not do any kind of product development, that kind of thing.
Yeah. So whenever if you don't go for to sort project funding,
Correct.
things are not go in a good way nowadays.
Yeah.
Nowadays.
True.
Whatever I can feel. So any other questions? I think that there is no other question. So
hello, sir.
Yeah.
Sir, I have one question.
Yeah.
Sir, where did you measure the antenna parameters?
Can you tell me actually
Like,
so many
sir,
antennas?
Like, sir, S parameter again, we have to measure, no, after fabrication.
Yeah.
Sir. So where did you, did the measurement?
Sir, actually, without measurement, how we can know your antenna is working properly?
Yes, sir, that's what I'm saying. You have done in your college or from somewhere else outside?
No. Actually, in our college, in our university, that measurement facility of that frequency 13 gigahertz is not available. We have done from the outside by giving payments.
Oh, acha. Yes, sir.
And in India, so many private parties are available, which are doing total antenna fabrication as well as measurement, but you need to pay a lot.
Okay, sir. Okay, sir. That's what I wanted to know.
Yeah, yeah.
Okay, sir. Thank you, sir.
Thank you. Any other questions from any participants?
So just an information, since some people are asking. Okay, I'm Dr. Shashi Kumar from Christ University. So we have an anechoic chamber facility which will cater up to 40 gigahertz. We can characterize your instruments if you have anything. So that facility we have, yeah, as a sir has already mentioned, it is going on a payment basis. So these
Yeah.
facilities we have up to, it will start from 800 megahertz to 40 gigahertz. The complete setup of 7 meter by 4 meter by 3 meter anechoic chamber facility we have with us.
Okay. So, sir, just can you tell me, do you have the facility for fabrication or only for measurement?
Fabrication, we have to go with a third party. We have a connection with a third party. He will do for us. Okay. And the boards, actually, he is not having different kinds of boards. Only he has FR4 and some easily available. Duride and all, if you have board, he can fabricate. That facility we have. But measurements up to 40 gigahertz, we can go. We have a full-fledged anechoic chamber with us.
Okay, sir. Thank you for your information. So,
Yes,
any
sir.
other
Okay, sir.
participants?
Thank you.
Yeah. Any other participants? Do you have any questions? So if no, then I will end my session for today, and tomorrow again, please come back at 6 p.m.
Okay, sir.
Okay.
Thank you.
Okay,
Thank you
sir.
very much.
Thank you, sir.
And thank you very much for your time.
Thank you, sir.
Thank you.
Thank you, sir.